A couple things we're going to cover in this video, and that is moments of inertia of composite areas. And some of those composites are going to be created with beams, and maybe beams with other things welded on top of them. We're also going to look at the product of inertia, principal axes, and Mohr's circle. Okay, so for these guys, it's just going to be a matter of understanding this table and how to get the information you need off of this table. So these are going to have some kind of interesting shapes. You can see this isn't quite a rectangle. And so the inertias and areas and center of mass, these are all going to be given for you. And the beams will be designated with some kind of a call letter. This is going to be related to their dimensions and what type of a beam they are. So W shapes versus S shapes, C shapes. And you're just going to find the correct beam over here. And then you can come and get the area of the beam. Remember, the parallel axis theorem needs the area times distance squared. So you'll need to know what that area is. It also has the dimensions of this thing, so the depth and the width of it. And here we have the inertias around the x-axis. This is given through the centroid of the beam. We have the radius of gyration, and we also have the inertia around the y-axis, where this is the centroidal axis. See that line above it? This is the inertia around the centroid. And if we attach other objects onto this, we can use the parallel axis theorem and these inertias around the centroid to calculate inertias of composite areas where part of that area is one of these beams. Okay, so let's go ahead and look at an example problem. So let's say you built a bridge and somebody didn't give you the right information for the wind load, right? So the thing is built and you find out the wind in that area is a lot more than originally was reported. And so the bridge is going to have to be modified to keep it from bending and breaking. And how you're going to modify it is you're going to just take some kind of a plate, right? And you're going to weld that on there. So we're going to look at adding this plate, and that plate is just a rectangle, right? So you have a 9" by 3/4 inch plate, and that thing is going to get welded on top of this beam, this green beam. And after you weld it on top, this composite area, so the green shape plus the yellow shape, it's going to have a new centroidal axis, and things tend to bend around the axis. So we're going to have to figure out where the location of that new centroid is and what the inertia is around that centroid. So how this thing is going to bend around this new location if these two guys are attached to one another. And inertia is additive, just like forces or any other vector. So we'll take the inertia of the green beam around that new axis plus the inertia of the yellow rectangle around that new axis. And we'll have to use the parallel axis theorem to get both of those pieces of information. Okay, so first thing we're going to do is figure out the location of the centroid, and then we will apply the parallel axis theorem to figure this thing out. And this is where we're going to go up to the table. So we were told what kind of a beam it was. So here's the W14 by 38 beam. And we need to figure out where the new centroid is. So remember how to calculate centroids. We're going to take the area of each piece. So the area of the plate, that's just going to be our 9 inches times 3/4 inches. There's the area of our plate. And then the area of our beam, we're going to get off of the table. So here's the area of the beam that you can get right off of the table. For the beam in the y direction, we're going straight down the center of this beam. So we don't need anything in the y direction. It's just going to be going straight up. But for the plate, we're going to look at this distance from the center to the top. And this is another thing that we're going to kind of look up in the table. So 14.1, that 14.1, that came out of the tables. So divide it by 2, and you get 7.05, and then we're going to go from the center of that beam to the center of that rectangle. So we're adding half of that 3/4 inch onto it, and now we have this distance from the center of the plate to the centroid of the beam. So what we're after here is we're kind of looking for the distance that the centroid is away from this original axis. So we're looking for x to x prime. So that's this 2.792 that we're getting. And this is, go back and review centroids if you don't remember how to get the centroid of something. So 50 divided by 17.95, and that will give us the centroid of the composite area. Okay, now that we know where this new axis is, we're going to get the inertia around this axis. Okay, so the inertia around this new yellow axis, and we will be using the parallel axis theorem. So for the beam, what we're going to do is take the inertia around the centroid, and this is what we're going to get from the table. So that 385 is from the table for this W beam, and then add the area of the beam. The area of the beam we also get from the table over here, times the distance from the old axis of rotation up to this new centroidal axis of rotation. So this was the centroid that we found in that previous slide. So we have the inertia around the centroid plus AD squared, and we have the inertia of the beam around that new axis. And then we can do the same thing for the plate. So if you look up the centroidal moment of inertia for a plate, that's that 1/12 base times height cubed. And this comes from just looking at what a rectangle is out of the tables for a rectangle, and the area of the plate. So that's going to be 9 times 3/4 of an inch. Add the distance from the center of the plate to the new axis. So we're going to subtract off that. Let me go to the previous slide here. So 7.425 from center to center, and then we're subtracting off that 2.792. So we end up with a 4.633 on here. So yeah, the real distances we're after is from the center of that plate to the new axis, and then from the center of the beam to that new axis. And with the centroidal inertias and those distances, we can get the inertia around the new object. And when we have both of these numbers, what we're going to do is just add them together. So we add the inertia of the beam together with the inertia of the plate. And here is the inertia around this new axis of rotation here. It's actually very interesting to compare the magnitude of what we have with the plate welded on versus what we have without the plate. So remember, without the plate, just on its own, was only 385. But then if we weld the plate on, we increase it from 385 to 618. So that means it's much, much more difficult to bend this I-beam with a simple plate welded onto it. So one little modification on this beam and you have significantly strengthened your structure with that. So that's great. And once you have the moment of inertia, you can go ahead and get the radius of gyration of this thing too. So remember, inertia is equal to k squared times a, and so k is equal to square root of I over a, and you can get your radius of gyration of this thing as well that you can report. Okay, so that's composite areas and looking at different types of beams. And when you get those tables, compare the different beams, the dimensions, and how hard one of them is to bend versus another. And again, this is something that you'll see again in mechanics and materials class too. Okay, so there's a couple of different examples in your notes that you can go through. Here's two beams that are welded together, and you have a similar homework problem in there that you can use some of these tables with too. The product of inertia, let's go through the equation for this first, and then we'll talk about where we use this quantity. So remember, the inertia we dealt with before was r squared m. R squared m was kind of the generic form, or in 2D it was r squared a. For the product of inertia, instead of r squared a or x squared a or y squared a, it's going to be x. So the distance away from the y-axis times y, the distance away from the x-axis, times our area element, dA. So a little bit different. Instead of x squared or y squared, we have x times y dA, and that's the product of inertia. A couple of things to note about this. If we're dealing with an axis of symmetry, so like half is above the x-axis and half is below the x-axis, when you have half above and half below and integrate that, it's no longer squared. So these negative signs do not go away, and what's above and below cancel out with one another, and it ends up being 0. So IXY ends up being 0 for axes of symmetry. Another thing to note is the parallel axis theorem applies for the product of inertia just like it did for IX and IY. So if you know the inertia around the centroidal axes, so here's the red axis and it goes through the centroid of the object. And let's say instead of rotating around the centroid, I want to rotate around this new black axis. So you can go between two different coordinate systems with that parallel axis theorem, where you're looking, instead of y squared or x squared, it's the distance from the new axis of rotation to the centroidal axis times the area of your object. So parallel axis theorem applies for products of inertia just like the regular area moments of inertia. This gets into why we would use this. Okay, so let's say that we want to rotate our object not around this black axis, but instead around this rotated red axis. So it's not parallel, it's rotated. And what this is going to turn into is not just looking at the moment around one rotated axis, but looking at how hard is it to rotate around all the different orientations and all the different axes. And the important question is, what is the hardest direction to rotate it around, and what is the easiest direction to rotate it around? So not parallel axis, but something that has been rotated. So we're going to go from rotating it around the x-axis to some new axes. Okay, trying to go back and forth between these two coordinate systems, and maybe you've done a little bit of this in some of your math classes, but let's say we have some area element dA. Okay, so I have some point, and I'm going to describe that point with respect to my new coordinate system. How would you do that? And what you would do, so here is, see this new length here? I'm trying to get this new length in this x direction as a function of what it was from my old coordinate system. And if I know this angle that I'm rotating it through, there's a couple different triangles that we can pay attention to here. So let's go ahead and look at these two orange triangles. So we have the same angle here as we have on this other orange triangle. And if I'm going to look at that coordinate system with respect to what my old black system was, okay, so this is my x distance, then I have two segments I'm going to add together here. So I'll add together x cosine theta and y sine theta. And if I add those two lengths, then I'll get the distance that I'm now traveling in this new coordinate system orientation. Okay, so I can describe the new coordinate system in terms of the old coordinate system using that angle that we've rotated through by. And you can do that in the x direction. You can also do it in the y direction. So we can go back and forth describing things in both of those coordinate systems. Here is the y direction. So if I want to go up in this direction, you'll see it's this big long distance minus this short distance. So you can see it's y cosine theta, that's this long chunk of it, minus x sine theta. And the difference between those two would be the new distance in this new coordinate system. So that little prime, this is the red coordinate system. Okay, so going back and forth between these two coordinate systems, we can use that in calculating our moment of inertia. And if you crank through this stuff, you can get the inertia around the new axis. So this is x prime, this is the rotated coordinate system, and show that the inertia around this new axis is actually related to the inertia around the old axes. So this would be the black coordinate system. So I can look at the inertia around the black ones, and if I have Ix and Iy, I can actually relate those two inertias to one another. And if you look at these equations, they end up following this circular pattern. And the circular pattern is known as the Mohr's circle, and it relates the inertias around differently oriented axes. So here we have the inertia around the new primed axis. Here's our I average, Ix plus Iy over 2, and it behaves like a circle where the radius of the circle is kind of the difference between these two guys, and this is where the product of inertia really comes into play. And when you get into dynamics, three-dimensional problems, the product of inertia becomes a mathematical construct that you're going to use there too. So the product of inertia, there's not really a physical significance to it, but it is very helpful in transforming inertias from one oriented coordinate system to another coordinate system. And that's going to be the main use for this Ixy, the product of inertia, is going back and forth between rotating around one axis versus a rotated coordinate system, rotating around a different axis. Okay, let me draw out this circular relationship for you so you can see how this maps out. And it's a really good idea to actually graph this thing out. So what we're going to do is we're going to plot Ix on one axis. So this is the inertia around the new oriented system versus the product of inertia we're going to put on the y-axis. And we'll look at where our average inertia is going to be the center of this circle. And every point along the circumference of this circle will represent the inertias rotating an object around a different axis of rotation. One thing to note, the angles represented on the circle are 2 times what the angle is to rotate the coordinate system. So going from A to B, there's 180 degrees between them. That would actually show up as only 90 degrees. So if I have IX on one side and I have IY on the other side, I'll show you. Even though that looks like 180 degrees between them here, it actually shows up as only 90 degrees between them on the coordinate system. Okay, but once you map it out on here, you can figure out the angle and you can figure out the inertia around any coordinate system. Let's work through an example for this one. That's where you'll see how this thing maps out, is just using an example. So here's an example. This is similar to the example that is in your homework. So we have an object that is made up of several rectangles. And we know what the inertia is with respect to this original X and Y coordinate system. So we have IX and IY, where this guy, let me highlight that. So we're looking at the inertia around this original coordinate system. There's IX. And then we can look at it around IY. So that's the second one. We're going to need to get IXY for this thing too. So the first thing, let's get IXY, and then we're going to map this thing out on a Mohr circle, and we will find the principal moments of inertia. And again, the principal moments of inertia, this is talking about what orientation is going to be hardest to rotate around and easiest to rotate around. And remember what we know about inertia. Okay, so the generic form of inertia is just like r squared m or r squared a. It's highly dependent on our radius. So think about an ice skater pulling their arms in. The smallest inertia is going to be where we have the smallest radius. So that's like pulling your arms in. So if you think about this shape up here, if we're going to sketch in an axis where the mass is kind of really hugged up around that thing, the minimum is going to occur somewhere in this direction. And then the maximum, so where it would be hardest to rotate, would be something that would be perpendicular to that minimum axis. So this is not actually calculating it. This is just eyeballing it. But the idea is we want to find this min or max. These are the principal axes of rotation. And to do that, we're going to have to rotate that original coordinate system some angle. And we want to figure out what that angle is. And we're going to use the Mohr circle in order to do that, to find this angle. Okay, so first we're going to find the product of inertia. That's needed for plotting out that Mohr circle, and then we will go ahead and find those axes. Okay, so first thing is to find the product of inertia. So we're going to split this into 3 rectangular areas. So we have area 1, area 2, area 3, and to get the inertia of 1 and 3, since these are not going through the x-axis, their centroid is not on the x-axis, we'll be using the parallel axis theorem for 1 and 3, and then adding those 3 shapes together to get the total inertia. This might be an application for Excel, to set up in Excel. So you just take the area of each piece So in this case, 3 times half an inch, 1.5 inches squared. And then we're going from the centroid to the center of each piece. And so this guy, we're going from the centroid of 1, there's our 1.75, so going up, and then we're going to go over. So here's our 1.25. And if we multiply x times y times a, again, this isn't y squared or x squared, it's just x times y times a, and then add these two together, that is our product of inertia. So not too bad. It almost feels like calculating the centroid of something, right? So it's a little bit different. 1.5 times 1.25 times 1.75. We're doing that twice. And the central region already goes through the centroid, and so that ends up being 0. So remember, the product of inertia for a symmetrical object around its centroid is 0. So we just have that first and third block that contribute to the product of inertia, so you just add it straight together. Okay, so now we have everything we need to plot this on the Mohr's circle. The problem statement gave us Ix, it gave us Iy. Now we have Ixy, and we're going to graph it out. So here we go. We have, let me highlight where this is showing up. So the inertias are going to show up on the x-axis. So instead of plotting this xy, this is like the x coordinate here. So we're going to go over 10, and then for Iy, that is going to be this guy right over here. There's Iy. So this is the x coordinate of this thing. And then the product of inertia, this is what's going to be plotted on our y-axis. So we have 6.56 and negative 6.56. You're going to make one of these guys positive and one negative. And so this point on the Mohr's circle represents how hard it is to rotate around the original black axes. And what we want to find is the principal axes. Okay, so this is around that originally oriented coordinate system. The max and the min point are going to be right here where Ixy ends up being 0. So if we rotate our black axes up to where our principal axes are going to be, that's what we're after. And it's a circle. So if we can find the center of the circle and the radius of the circle, then we can very easily know where every point on there is. Okay, so here's the center. We're just taking the average between these 2 points. So 10 plus 6.97 divided by 2 is 8. So there's the center of our circle. To get the radius of our circle, so we're looking at kind of just an a squared plus b squared equals c squared, right? So from top to bottom, and we can make a big triangle or a small triangle, but you can figure out what the radius of this circle is from the coordinates of it. And then once you have the radius, you also can figure out what the angle is. Right? So, and remember, the angle that shows up on the Mohr's circle is actually twice the angle that you rotate the coordinate system with. So this 2 theta m, that's twice what we will actually rotate this with to see where that principal axis lies along our shape. Okay, so we have tangent is opposite over adjacent. The opposite side of this big yellow triangle, we have 2 times that product of inertia going up on this opposite side, and then along the base is the difference between this 10 and the 6.97. So between the 2 of those, we can figure out what our angle is, and we can find what our principal moments of inertia are. So here's the max. That's going to be along this A direction, so that's the hardest inertia, a hardest location to rotate around. And then here is our minimum. So we're just subtracting from the center of the circle down radius to find the minimum. And that's going to describe this B orientation for rotating around it. Okay, so here's the max and the min. And you can see that the max, so this red one is 15. And the min is only 1.9, so much, much smaller. And this is, so for if you have something that is going to be moving around or bending, you want to see what it wants to bend around so that you can maybe support that or just know what it wants to bend around. So these principal moments of inertia, these are very important things to understand. And it's a really neat thing that these guys map out with this circular relationship. And all you have to do is know the inertia around one orientation and the product of inertia, and then you can figure out any orientation you want. So every single point on this circle represents the inertia around some different orientation. So you can orient this thing any way you want and get all of the inertias of the whole thing. So you either have the parallel axis theorem to go between axes that are parallel to one another, or you have the Mohr's circle to relate axes that are rotated from one another. Okay, that's the end of it. And this is, yeah, the moment of inertia really is an important thing. You'll see this in your physics class if you haven't already. You'll see it in dynamics again, and also in mechanics of materials. You'll also see the moment of inertia.